Hey guys, we're going to work out the electric potential for a disk of charge. Okay, so this is very similar. This has a very similar geometry to the ring example, which we just finished, but the charge is spread out a little differently. So I'll go ahead and draw really the same basic shape. Okay, so I have a outer radius r, and then I have, we're going to ask for we're going to try to find the potential at a point over the center of it. But we're going to change things rather than concentrating all the charge along the outer edge. We're going to imagine the charge is uniformly distributed throughout. So immediately we know that we have to change the density that we use. So if a ring is parameterized by just an angle, so it's a 1D shape, a disk is parameterized by an angle and a radius. So that takes two parameters to describe a point on the disk. Therefore, it is a two-dimensional surface. And if I were to, so when we had a ring, we broke up little line segments. In this example, what we're actually going to do is break out little postage stamps. And we're going to break out little postage stamps of charge and kind of add up their effects separately. But we treat each one essentially like it's a point charge and then integrate. So when we talk about the position of a source charge, we're talking about the position of this little postage stamp from the origin. Okay. So let's go through. It's really the same kind of analysis that we had before. So we're going to say that, well, okay, how much charge do you have there? Oh, sorry, I should go back here. Our general formula is going to be, go back to black for that. The general formula is as always, that the potential equals the integral of dq over 4 pi epsilon naught divided by the distance from the source charges to the place where you might make an observation, RSO, the relative vector. So in this problem, with this picture, this would represent RS. This would represent RO, and this would represent RSO. Okay, the RSO would be from the source to the observer. Well, we can see from the picture here that the magnitude of RSO is going, because it makes a right triangle, is going to be little r squared. Remember, this little postage stamp could be at any radius. And in fact, eventually when we do the sum, it'll be at all, sum over all possible configurations. So it'll be a lowercase r, just to remind us that it's a variable. So it's any radius. So the hypotenuse will be little r squared plus z squared. Take the sum and square root. Or if we want to be a little bit more formal, what we could do is we could write it out as RS vector is little r, r hat, not big R, because this postage stamp doesn't live all the way on the edge of the ring, it lives in the middle. And I would have RO as Z hat. I have RSO would be Z hat minus R hat. And I would have the magnitude of RSO. It would be Z squared plus R squared, take the square root. And that comes from thinking of taking the dot product with itself and then taking the square root, and the dot product of, then when you do the cross term between the z hat and the r hat, you get 0. So that's the final form. It's the same as what we found, or what you can find from this picture. Okay, so that is the denominator. We still have to work out dq. So to find dq, well, we have charge. It's spread out over a surface area. So the surface area of a little patch we call dA. So we're going to say that the charge density is a surface density, sigma, times dA. And we all remember from Calc 3 that sigma, sorry, the dA is equal to R dr d theta. All right. So when we had a ring, we were able to pull RSO out of the integral. We can't do that here. And it makes sense because as you move around on this disk, R is variable, lowercase r is variable, but R is one of the things we are integrating over. So that means that our distances are all going to change as you walk around, on the disk. All right, so let's plug in. Take all these little pieces. So we want to pull in this bit and this bit, drop them in, and see what's left. 1 over 4 pi epsilon naught times the integral. Now I have a double integral. And I'm going to integrate from theta equals 0 to 2 pi. Nothing depends upon theta. That integral is trivial. And the radius integral is going to integrate from 0 to big R. And my dq is going to give me a sigma r dr d theta. Sigma is going to pull out if we assume it's constant. R dr d theta divided by this quantity, the square root of r squared plus z squared. Okay, so we have to perform that integral. The physics is really done at this point. Maybe at the very end we can check that we get the right answer, just that it has the, because it should have the appropriate limit when z goes to infinity. It should look like a point charge. But the real work is just mathematics. So let's first do the theta integral. That's trivial. That's going to give me 2 pi sigma 4 pi over epsilon naught is out front. And then I have to do an integral from 0 to capital R of r dr over the square root of r squared plus z squared. Now you can do this in lots of ways. You can use u substitution, make u equal to r squared plus z squared. And then du would be 2 r dr, so you get a factor of a half, but basically it's done for you. So that would work. So you could say u equals r squared plus z squared, and take du equals 2r dr. That would be fine. Or it's a little faster for me mentally just to look at it and think to myself. So I look at it and say, self, what function has this as a derivative? I look at it, and I think, oh, this, I say r over the square root of r squared plus u squared looks like a derivative acting on r squared plus u squared. Let's think about that. If I take this derivative, you get a 1 over square root, blah, blah, blah. And then the chain rule, and you get a half because it was a half power. And the chain rule says you have 2r. And the 2 cancels the half, and you get exactly that. So I can say that this integral is 2 pi sigma divided by 4 pi epsilon naught times the integral from 0 to r of d by dr acting on square root of r squared plus u squared. Oh, I apologize. It shouldn't be u squared. It should be z squared. Getting sloppy here. If you don't see this, just go through the u substitution. It'll work out. And I have to integrate it dr. But because this is a total derivative, and the integral of a total derivative is just the difference of the integrand, or the differentiated function evaluated at the upper limit minus lower limit, I can write this as 2 pi sigma over 4 pi epsilon naught times evaluate at the upper limit minus the lower limit. So that's going to be square root of r squared plus z squared minus square root of z squared. Okay? Is that okay so far? I hope so. All right. Here so you can still see it. I'm just going to rewrite this and clean it up a little bit. So if I wanted to, if I wanted to write the answer in terms of sigma, you could cancel the 2 pi's and be done. I'd like to write it in terms of the total charge. The total charge for a disk of constant charge density would be sigma times the area. So that means sigma equals total charge divided by pi big R squared. So that's how I'm going to write this. And the other thing I'm going to do is, morally speaking, I wanted to call this Z. And the way I drew the picture, it even works for Z. But really, it should be absolute value. So let's be just a shade more careful. Okay, so then I can write out the potential due to a disk at position 0, 0, Z of constant charge density would be, keeping all the little bits here and there. So I'm going to get Q over 2 pi R squared times the square root of R squared minus Z squared minus the absolute value of Z. All right. So I think I've got all the little pieces there. Oh, and I forgot my epsilon naught. Always forgetting something. I hope I didn't forget it in the last example. If so, you may need to go back and check your notes. So let me check here. That gives me a 2. Yes, that's correct. All right. So that is a formula for the potential. And then how can I tell if this is correct? Well, let's take a limit. Let's imagine Z is really big. So Z, I apologize, there's a plus in there. If Z is very, very, very large, I can think of this piece if z is very large, I can factor that out, and this becomes magnitude of z times the square root of 1 plus r over z squared, which is, to good approximation, magnitude of z plus r over z squared, and there's a factor of a half coming from the square root. So if I were to substitute for z, when z is large, or z much, much bigger than r. So when I substitute that into here, so if z is much, much bigger than r, this becomes v equals q over 2 pi r squared epsilon naught. And I have z plus something minus z. So these two z factors would cancel, and I would get r squared over z squared with a half. And I see that the r squareds cancel, and the half combines with the 2 to give me a 4. And sure enough, I have, cancel the r's here, I have q over 4 pi epsilon naught times 1 over z squared. It looks like a point charge when z goes off to infinity, as it should. And that just gives me confidence that this, in fact, is the correct answer. Okay, so that's for a ring and a disk. And that's all we're going to calculate using the brute force method. Okay, next up, I'm going to remind you of the relationship between electric field and electric potential using gradients and integrals. And then after that, we're going to use that to calculate other configurations.